Imagine being so certain about a solution that could save your country thousands of hours and countless lives, yet nobody in power will listen to you. Not because your idea is bad, but because you are just a regular worker. What would you do? Give up and go back to your daily routine? Or risk everything you have to prove the world wrong? This is the true story of a man who chose the second option, and in doing so, he altered the course of World War II. His invention was so brilliantly simple that it seems almost ridiculous nobody thought of it sooner. Yet this simple idea would save more time than 5,000 years of non-stop work. And the man behind it? An $11 a day welder that the Navy told to shut up and follow orders. Let me take you back to March 1941. The calendar reads March 15th. It is a cold morning in Vallejo, California. The fog rolls in thick from the San Francisco Bay, and through that fog, you can hear the constant hammering, welding, and shouting of 12,000 workers at Mare Island Naval Shipyard. This is not just any shipyard. Founded in 1854 by Commander David Glasgow Farragut, Mare Island holds the distinction of being the very first United States Navy base established on the Pacific Ocean. By 1941, it has evolved into the premier West Coast facility for building submarines. The yard stretches across 635 acres along the Napa River, about 25 miles northeast of San Francisco. At this moment in history, Mare Island operates around the clock. 3 shifts of workers, 7 days a week. There are no days off. There is no slowing down. Everyone here knows what is coming. War. The newspapers are full of it. Japan is expanding across China and Southeast Asia. Germany has conquered most of Europe. The United States is trying to stay neutral, but that neutrality is crumbling fast. American destroyers are already fighting undeclared battles with German U-boats in the Atlantic. President Roosevelt has instituted a military draft. Young men are being called up by the hundreds of thousands. And here at Mare Island, the Navy is desperate to build submarines as fast as humanly possible. The problem is that building a submarine takes time. A lot of time. From laying the keel to launching the finished boat, you are looking at 12 to 18 months under the best circumstances. And right now, circumstances are far from best. There are shortages of materials. Shortages of skilled workers. And most frustratingly, outdated construction methods that waste enormous amounts of labor. Among the 12,000 workers at Mare Island is a man named Theodore Edward Nelson. Everyone calls him Ted. He is 36 years old, California born and raised. He has the weathered hands and permanent squint of a man who has spent his entire adult life working with metal and fire. Ted is a welder, employee number 3872. He earns $11 per day working the day shift from 7 in the morning until 4 in the afternoon. $11 a day is decent money for a welder in 1941. It is enough to rent a small house in Vallejo, feed his wife Emma, and maybe save a few dollars at the end of the month if they are careful. But Ted is not thinking about his paycheck right now. He is standing in the cramped interior of a submarine under construction, and he is angry. Not the hot, explosive kind of anger. The cold, simmering kind. The kind that comes from watching something stupid happen over and over again, knowing there is a better way, and being completely powerless to change it. Around him, 12 men are working to install wooden deck planks. Yes, you heard that right. Wooden planks. On a submarine. This might seem strange at first. Why would you put wood on a steel submarine? But there are actually good reasons. Wood provides better traction than steel when it gets wet from rain or sea spray. Wood is much quieter than steel when sailors are walking around on deck, which matters a lot when you are trying to be stealthy. Wood provides some insulation against the freezing cold steel beneath it. And if there is ever a fire on deck, wood can be quickly torn out and thrown overboard, whereas welded steel plates would require cutting torches and hours of work to remove. So wooden decks make perfect sense. The problem is not the wood itself. The problem is the absolutely insane method the Navy requires for attaching that wood to the steel framework of the submarine. Let me walk you through the process so you can understand just how ridiculous it is. First, workers take the wooden planks, which are typically about 2 inches thick and maybe 10 inches wide, and they drill holes through them at precisely measured intervals. These holes have to be in exactly the right spots because they need to line up with corresponding holes in the steel framework below. The holes are then countersunk, which means the top part of each hole is widened so that the head of a bolt can sit flush with the surface of the wood. Next, the workers carry these heavy planks into the submarine and position them on top of the steel deck framework. Getting the planks into position is tricky because the submarine interior is cramped and filled with equipment, pipes, and cables. But positioning the planks is actually the easy part. Now comes the nightmare. Here is where it gets truly absurd. In order to attach these planks, workers need access to both sides of the steel framework. The top side and the bottom side. The top side is no problem. That is where the planks are sitting. But the bottom side. That is inside the submarine, in the compartments below the deck. These compartments are maybe 4 or 5 feet high in most places. Some spots are even more cramped. So here is what the Navy procedure requires. Before you can install the deck planks, you have to build extensive scaffolding structures inside the submarine compartments below the deck area. These are not simple scaffolds. They need to be strong enough to support multiple workers. They need to have platforms at the right height so workers can reach the underside of the steel framework. And because the submarine interior is full of obstacles like pipes, bulkheads, and equipment, the scaffolding has to be custom built to fit around everything. Building this scaffolding takes a team of workers about 2 full days. 2 entire days just to build temporary structures that will have to be torn down again when the job is finished. Once the scaffolding is finally ready, the actual deck installation can begin. Workers up top on the main deck push long threaded bolts down through the holes in the wooden planks. These bolts pass through the planks and continue down through corresponding holes in the steel framework below. The bolts are usually about 4 to 6 inches long. Meanwhile, workers down below are standing on the scaffolding platforms in those cramped, dark, uncomfortable compartments. Their job is to catch the bolts as they come through, thread nuts onto the protruding ends, and tighten everything with wrenches. This requires perfect coordination between the crew above and the crew below. If the holes do not line up exactly, the bolt will not pass through and they have to reposition everything and try again. If a worker below drops a nut, it falls through the scaffolding and somebody has to climb down, find it, and bring it back up. If a wrench slips, which happens constantly in cramped spaces, knuckles get smashed against steel. The whole process is painfully slow. For a typical section of submarine decking, maybe 20 feet by 30 feet, you are looking at several hundred individual bolts. Each bolt requires multiple steps. Position it from above. Catch it below. Thread the nut. Tighten it. Check that the plank is sitting flush. Tighten some more. Over and over and over. A typical submarine has several hundred square feet of wooden decking that needs to be installed this way. The main deck. The conning tower platform. Interior walkways. All told, you are looking at thousands of individual attachment points. For a single submarine, the complete deck installation requires a crew of 12 to 16 men working for 5 to 7 days. And remember, 2 of those days are just building and then dismantling the scaffolding. The actual bolt installation takes up the rest of the time. Ted Nelson has done this job dozens of times over the past year. He has spent countless hours standing on scaffolding platforms, hunched over because there is not enough headroom to stand up straight, threading nuts onto bolts in compartments that are barely 4 feet high. His back aches constantly from the bending. His knuckles are covered in scars from wrenches slipping and smashing into steel pipes. His patience is long gone. But Ted is not just frustrated about his own discomfort. He can see the bigger picture here. War is coming. Everyone at Mare Island knows it. The newspapers say it is only a matter of time before America gets dragged into the fighting. When that happens, the Navy is going to need submarines. Lots of them. As many as the shipyards can possibly build. Every day matters. Every hour matters. And here they are, wasting an entire week per submarine just to install wooden deck planks using a method that has not changed since the First World War. The yard is already behind schedule. The Navy wants submarines in the water, ready to fight. But boats keep sitting in dry dock, waiting for deck installation to be completed. Waiting for scaffolding to be built, waiting for workers to thread thousands of nuts onto thousands of bolts in cramped spaces below deck. It is maddening. And the worst part? Ted knows there is a better way. He has been thinking about this problem for months now, turning it over in his mind during the long hours of routine welding work. The solution seems so obvious to him that he cannot understand why nobody else sees it. Instead of bolting from above and threading nuts from below, why not just weld attachment studs directly to the steel framework? Weld them from one side only. From above. No scaffolding required. No nuts and bolts. No workers cramped in compartments below. Just fast, strong, permanent welds. The concept is beautifully simple. A threaded stud, which is basically just a bolt without a head, could be welded directly to the steel deck framework in a fraction of a second. Then the wooden planks, which would have threaded inserts or specialized nuts embedded in them, could simply be screwed down onto these pre-welded studs. The entire operation could be performed from the top side only. No scaffolding. No below-deck work. No coordination between crews working above and below. One worker with a welding gun could do in one day what currently takes 12 workers a week to accomplish. Ted has actually seen stud welding before, in a very limited form. The technology exists for welding studs onto flat horizontal steel plates. Here is how it works. You place a small pile of flux powder on a flat steel surface. Flux is a chemical compound that helps create a clean, strong weld by removing impurities. You position a metal stud in the pile of flux. Then you create an electrical arc between the stud and the steel plate. The intense heat of the arc melts both the bottom of the stud and the surface of the plate. They fuse together. When the metal cools, you have a permanent weld. The whole process takes less than a second. The problem is that this method only works on horizontal flat surfaces. Why? Because the flux is loose powder. If you try to do this on a vertical wall, the flux powder just falls off before you can create the arc. If you try to do it on an overhead surface like a ceiling, the powder falls down onto your head. The loose flux powder needs gravity to hold it in place, so it only works when welding downward onto a flat surface. This is a huge limitation. On a submarine or ship, you need to weld in every direction imaginable. Vertical walls, overhead ceilings, angled surfaces, underneath overhangs. Every weird angle you can think of. If stud welding only works on flat horizontal surfaces, it is basically useless for shipbuilding. Welding engineers have been trying to solve this problem for 20 years. Companies have spent thousands of dollars on research. Engineers with fancy degrees from prestigious universities have proposed elaborate solutions involving magnetic flux holders, vacuum systems, and complex mechanical jigs. None of it has worked well enough to be practical. But Ted thinks he has the answer. And it is so simple, so obvious, that when the solution first came to him, he almost laughed out loud. Instead of using loose flux powder, encase the flux in a small ceramic cap. Just a little ceramic shell that fits on the end of the stud. The flux is inside the cap, held in place. Now it does not matter what angle you are welding at. Vertical, horizontal, overhead, upside down. The flux stays exactly where you need it because it is trapped inside the ceramic cap. He can picture the whole system in his mind. A handheld welding gun shaped roughly like a pistol. A spring-loaded mechanism inside the gun that holds the stud and presses it firmly against the steel surface. An electrical trigger that creates the welding arc. And most importantly, a disposable ceramic flux cap attached to the end of each stud. You load a stud into the gun. You press the gun against the steel where you want the stud to go. You pull the trigger. The electrical arc melts the end of the stud and the surface of the steel. They fuse together. 1 second. Done. Move to the next spot. One worker could install dozens of studs in the time it currently takes to install a single bolted connection. The time savings would be enormous. and the welds would actually be stronger than bolted connections because there are no threads to strip, no nuts to come loose, no bolts to corrode. Ted is so excited about this idea that he can barely sleep at night. He keeps sketching designs in a worn notebook he carries in his back pocket. Different gun mechanisms. Different flux cap designs. Different stud shapes. He is convinced this will work. He is absolutely certain of it. So he decides to bring his idea to the people in charge. Surely they will see the value in this. Surely they will want to implement a method that could save thousands of hours per submarine. He requests a meeting with his immediate supervisor, a Navy lieutenant named Morrison. Morrison is a career officer, maybe 40 years old, with the kind of by-the-book mentality that the Navy loves. Everything has to follow regulations. Everything has to be done according to established procedures. The meeting takes place in Morrison's small office overlooking the shipyard. Ted brings his notebook with the sketches. He explains the concept. He shows how the ceramic flux cap would solve the angle problem. He estimates the time savings. He talks about how many more submarines they could build. Morrison barely looks at the sketches. He interrupts Ted after maybe 3 minutes. "We have established procedures, Mr. Nelson. The Navy has specifications for deck installation. These specifications have been developed over many years by qualified engineers. We follow those specifications. That is how the Navy works." "But sir," Ted says, "this would save so much time. We could build submarines faster. We need submarines. The war is coming and we need boats in the water." Morrison's expression hardens. "Mr. Nelson, your job is welding. You are paid to weld according to the methods specified in your work orders. You are not paid to redesign Navy procedures. If you want to weld instead of supervising bolt installation, stick to your current assignments." This meeting is over. Ted leaves the office frustrated but not defeated. Maybe Morrison is just too rigid. Maybe he needs to talk to someone with more technical understanding. He requests a meeting with the shipyard's chief welding engineer, a civilian contractor named Hartwell. Surely an engineer will appreciate the technical merit of the idea. Hartwell is more polite than Morrison. He actually looks at the sketches. He asks a few questions about the flux composition and the welding current requirements. For a moment, Ted feels hopeful. Then Hartwell sets down the notebook and shakes his head. "Son, people much smarter than you and me have been trying to solve this exact problem for 2 decades. If it was as simple as putting flux in a ceramic cap, someone would have done it already. The big welding equipment companies have entire research departments working on this. Do you really think you have figured out something they have missed?" "But I have tested it," Ted protests. "Well, not exactly, but I have thought through all the technical details. I am certain it would work." Hartwell gives him a sympathetic look. "Even if your idea is sound, and I am not saying it is, the Navy has specifications. We cannot just change procedures because a welder has an idea. You would need approval from the Bureau of Ships in Washington. You would need engineering studies, metallurgical analysis, prototype testing, failure mode analysis. That process takes years. Literally years. You would need to submit a formal proposal. It would go through multiple review boards. Every step would require documentation and approval. We do not have years," Ted says, his voice rising slightly. "We need submarines now. Everyone knows war is coming. Japan is building warships. Germany is building U-boats. And we are wasting entire weeks per submarine because of outdated attachment methods." Hartwell spreads his hands in a gesture of helplessness. "That is not my problem, Mr. Nelson. My problem is building boats according to approved specifications. Your problem is doing the welding work you are paid to do. I appreciate your enthusiasm, but you need to understand how things work. Innovation in military construction moves slowly. That is just reality." Ted walks out of that meeting angry. More than angry. Furious. He has offered them a solution that could revolutionize submarine construction. A solution that could save thousands of hours per boat. And they have dismissed it without serious consideration. Not because the idea is flawed. Not because it would not work. But because he is just a welder. Because innovation requires paperwork and approvals. Because following established procedures is more important than winning the war that is about to start. But Ted is stubborn. His wife, Emma, sometimes jokes that he is too stubborn for his own good. He decides to try one more time, going as high up the chain as he can. He writes a formal letter to the shipyard commander, Captain Thomas Withers. The letter takes him 3 evenings to compose. He writes draft after draft, trying to strike the right tone. Respectful but urgent. Technical but understandable. In the letter, he carefully explains the current deck installation process and its inefficiencies. He describes the scaffolding requirements, the labor costs, the time delays. Then he explains his stud welding concept in detail. The ceramic flux cap. The handheld welding gun. The elimination of below-deck work. He includes rough sketches and calculations estimating that his method could reduce deck installation time from 6 days to 1 day, and reduce the crew size from 12 workers to 3 workers. He concludes the letter with a direct appeal. Sir, war is coming. We all know it. When that war begins, America will need every submarine we can build. My method can help us build submarines faster. I am not asking for money or recognition. I am asking for the opportunity to demonstrate that this works. Give me 1 week and some scrap steel, and I will prove it. He submits the letter through proper channels, as Hartwell had explained. Worker suggestions are supposed to go to the suggestion committee, which reviews them and forwards worthy ideas up the chain of command. 3 weeks pass. Then Ted receives a reply. It is a form letter, professionally typed on official Navy stationery. Dear Mr. Nelson, thank you for your interest in improving shipyard efficiency. All technical proposals are carefully evaluated by the Bureau of Ships Engineering Review Board in Washington. Your suggestion has been forwarded for consideration. Please be advised that the review process typically takes 18 to 24 months due to the thorough engineering analysis required for any changes to established procedures. You will be notified if your proposal is approved for further study. Thank you for your service to the Navy. 18 to 24 months. 2 years. By then, the war might already be over. Or America might have lost because we did not have enough submarines. Ted crumples the letter and throws it in the waste bin in the corner of the welding shop. That evening, sitting at the small kitchen table in his house in Vallejo, Ted makes a decision that will change his life forever. Emma is washing dishes at the sink. The radio is playing big band music quietly in the background. Ted sits there staring at his notebook full of sketches, and he realizes something. The Navy is never going to listen to him. They are too bureaucratic, too slow, too invested in doing things the way they have always been done. If he wants this invention to exist, if he wants to prove that it works, he is going to have to do it himself. He is going to have to quit his job, take his life savings, build a prototype, prove the concept. Then maybe, just maybe, people will pay attention. It is a terrifying decision. He has a steady job that pays $11 a day. That is more than many people make. The country is still recovering from the Depression. Millions of people are unemployed. And he is thinking about quitting to pursue what everyone has told him is a crazy idea? Emma, he says quietly. She turns from the sink, drying her hands on a towel. I have been thinking about my welding idea. Ted, we have been through this, she says with a sigh. The Navy is not interested. You tried. Maybe it is time to let it go. I cannot let it go, he says. I cannot watch them waste time and resources when I know there is a better way. So I am going to build it myself. Emma sits down across from him. What do you mean, build it yourself? I mean quit my job. Use our savings. Build a prototype welding gun. Prove that it works. Then sell it to shipyards. Emma stares at him for a long moment. Ted, we have $400 in savings. That is all we have. If you quit your job and this does not work, we will have nothing. If I do not try this, I will regret it for the rest of my life, Ted says. I know this will work, Emma. I know it. And war is coming. When it does, my invention could help. It could really help. How can I just let it go? Emma is quiet for a while, looking at her husband. She has been married to him for 12 years. She knows that look in his eyes. He has made up his mind. What do you need from me? She asks finally. I need you to trust me, he says. Just for a little while. If I can build a prototype and show that it works, companies will buy it. I am sure of it. Emma reaches across the table and takes his hand. Okay. But promise me something. If this does not work, if you cannot sell your invention, you will go back to welding. Deal. Deal, Ted says. The next day, Ted goes out to the small garage behind their house. It is not much. Just a wooden structure with a dirt floor, barely big enough for a car if they had one, which they do not. But it has electric power. It has a workbench. It has enough space for what he needs to do. He starts collecting materials. Scrap steel from the shipyard, which workers are allowed to take home for personal projects. Old welding equipment from a friend who has upgraded his gear. Spring mechanisms from discarded machinery. Pieces of ceramic from a pottery supply shop in town. Copper wire for electrical connections. He spends every evening and every weekend in that garage, designing and building and testing. The welding gun design goes through multiple iterations. The first version is too heavy and awkward to hold. The second version has a spring that is too weak and does not press the stud firmly enough against the steel. The third version has electrical connection problems. Each failure teaches him something. Each problem gets solved. The flux cap proves to be the trickiest part. The ceramic has to be strong enough to protect the flux but thin enough to break away easily when the weld is complete. The flux mixture itself has to be precisely formulated. Too much of one chemical and the weld is weak. Too much of another and the arc does not form properly. He experiments with dozens of different recipes, adjusting the ratios bit by bit until he finds a mixture that works consistently. His neighbors think he has gone crazy. They see the lights on in his garage until late at night. They hear strange zapping sounds and see flashes of light through the cracks in the walls. One neighbor, an elderly woman named Mrs. Patterson, actually asks Emma if Ted is building some kind of electrical torture device. Emma just smiles and says he is working on a welding project. By early May 1941, after 6 weeks of work, Ted has a functioning prototype. It is crude. The gun is heavier than he would like. The trigger mechanism is a bit sticky. The flux caps have to be assembled by hand, which is tedious. But it works. It actually works. He sets up a test in his garage. He takes a piece of steel plate and props it up vertically against the wall. He loads a stud into the welding gun. He presses the gun against the vertical steel surface. He pulls the trigger. There is a bright flash and a sharp cracking sound. When he pulls the gun away, the stud is welded firmly to the vertical surface. He tries to twist it off with a wrench. It does not budge. The weld is solid. He tries it on an overhead surface, welding studs to the underside of a steel beam. Perfect. He tries it at weird angles. Perfect. Every single weld is clean and strong. And each one takes less than 1 second to complete. Ted wants to shout with excitement, but it is late at night and he does not want to wake the neighborhood. Instead, he just stands there in his garage, looking at the dozens of studs he has welded to test pieces in every conceivable position, and he allows himself a smile. He was right. The Navy engineers were wrong. This works. The next day, he brings the prototype to Mare Island during his lunch break. He finds a group of fellow welders eating sandwiches near the submarine construction bay. These are guys he has worked with for years. Practical men who understand welding and appreciate good tools. Hey, Ted says, I want to show you something. He pulls out the welding gun and a handful of studs with flux caps attached. Over the next 15 minutes, he demonstrates the system. He welds studs to vertical surfaces, horizontal surfaces, overhead surfaces. The welders crowd around, amazed. "Holy cow, Ted," one of them says. "That is incredible. How fast is that? Less than a second per stud?" "About half a second," Ted confirms. "And you can see it works on any angle. No scaffolding needed. No below-deck work. One guy could install an entire submarine deck in a day or two. This is going to save us so much time," another welder says, shaking his head in disbelief. "You need to show this to Morrison right away." Ted laughs bitterly. "I already showed Morrison. Months ago. He was not interested." "Are you kidding me? How could he not be interested in this?" "Because I am just a welder," Ted says. "And the Navy does not listen to welders." "Then quit and start your own company," a third welder suggests. "Sell these guns to shipyards across the country. You will make a fortune." This idea has honestly not occurred to Ted until this moment. He built the prototype to prove the Navy wrong, to force them to pay attention. But starting a company? Becoming a businessman? That seems like a completely different proposition. Yet the more he thinks about it over the following days, the more sense it makes. The Navy has made it clear they will not adopt his invention through official channels. But there are dozens of shipyards across America, and that number is growing every month as the country prepares for war. The Kaiser shipyards in Richmond are hiring thousands of workers. The Bethlehem Steel Shipyard in San Francisco is expanding rapidly. There are yards in Seattle, in San Diego, in Long Beach. All of them face the same labor shortages and production pressures. All of them would benefit from faster attachment methods. If he can make and sell his welding guns to these private shipyards, he can prove the concept works. And then, maybe then, the Navy will finally pay attention. On June 20, 1941, Ted Nelson walks into Morrison's office and hands him a letter. It is his resignation. Morrison looks up from his desk, surprised. "Nelson, what is this about? You are a good welder. We need good welders." "I am going to build welding guns," Ted says simply. "And when the Navy comes back asking to buy them, I hope you remember this conversation." He turns and walks out before Morrison can respond. He cleans out his small locker in the welding shop. He says goodbye to a few friends. He walks out of Mare Island Naval Shipyard for what he thinks might be the last time. It is a sunny California afternoon. He has $11 in his pocket, a garage workshop full of tools and scrap metal, and total confidence that he is doing the right thing. Emma is understandably nervous. They now have zero income. Their savings of $400 will not last long. But she supports her husband. She has always supported him. "If you believe in this, then we will make it work," she tells him. On July 1, 1941, Ted files incorporation papers for the Nelson Specialty Welding Equipment Corporation. The name sounds impressive, but the reality is less so. The company consists of Ted working in his garage, manually assembling welding guns from parts he fabricates himself. There are no employees, no office, no factory, just Ted and his tools. He needs capital to really get started. He needs to buy materials in bulk. He needs better equipment. He needs money for marketing and sales. After asking around, he learns about the Reconstruction Finance Corporation, a government lending agency established during the Depression to help small businesses get started. He prepares a loan application, including detailed technical drawings of his welding gun, estimates of production costs, and projections of potential sales. To his surprise and relief, the RFC approves a loan of $95,000. It is an enormous sum of money. More money than Ted has ever imagined having. The loan comes with strict conditions. He has to use it for business purposes only. He has to make regular payments. If the business fails, he is personally liable for the debt. But it gives him a real chance to turn his invention into a viable product. With the loan money, Ted rents a proper workshop space in Vallejo. Not a big factory, just a decent-sized commercial space with proper electrical service, good lighting, and enough room to set up assembly stations. He buys metal stock, ceramic materials for the flux caps, springs, electrical components. He designs simple manufacturing jigs that allow him to produce parts more quickly and consistently. By August 1941, he is producing about 2 welding guns per week. Each gun is essentially handmade. He cuts the metal parts on a lathe, assembles the internal spring mechanism, wires the electrical components, and tests each gun thoroughly before it leaves his shop. It is slow, painstaking work. But each gun works perfectly. Now comes the hard part. Sales. Ted has never been a salesman. He is a mechanic, a maker, a problem solver. The idea of cold calling potential customers makes him deeply uncomfortable. But there is no choice. If he cannot sell his product, the company will fail and he will lose everything. He starts with machine shops and small fabrication companies in the San Francisco Bay Area. He loads a welding gun and some studs into his truck. He drives to businesses, walks in, and asks to speak with the owner or foreman. Most of the time, he gets turned away at the door. "We are not interested. We have suppliers we already work with. We do not need new equipment." But occasionally, someone is curious enough to watch a demonstration. Ted will take them outside to the parking lot, pull out a piece of scrap steel, and show them how the system works. The reaction is usually the same. Initial skepticism followed by amazement when they see how fast and strong the welds are. By September 1941, Ted has sold 18 welding guns to various small companies around the Bay Area. It is not much, but it is enough to cover his loan payments and keep the business alive. He has also sold several thousand individual studs with flux caps. Some customers are buying repeatedly, which is a good sign. The product works. People who try it like it. He just needs more customers. Then on December 7, 1941, everything changes in an instant. Pearl Harbor. Ted hears about it on the radio. He is in his workshop, assembling a welding gun, when the regular programming is interrupted. We interrupt this broadcast for an urgent news bulletin. The Japanese have attacked Pearl Harbor in Hawaii. Multiple ships have been sunk or damaged. American casualties are reported to be in the thousands. The attack is ongoing. Ted stops working and listens to the radio for the next 2 hours as more details come in. Battleships sunk. Aircraft destroyed. Thousands dead. The president will address Congress tomorrow. War is certain now. His first thought is horror at the lives lost. His second thought, and he is a bit ashamed of this but it is true, is that everything is about to change for his business. America is now at war. Shipyards will be operating at maximum capacity. The government will be desperate for anything that speeds up production. His invention is about to become very, very relevant. He is right. Within 48 hours of Pearl Harbor, his phone starts ringing. Purchasing agents from shipyards all over the West Coast are suddenly calling. "We heard you make a stud welding system. We need to place an order. How quickly can you deliver?" The Kaiser shipyards, which are just beginning to ramp up for massive Liberty ship production, place an order for 50 welding guns and 10,000 studs. Bethlehem Steel orders 40 guns. Moore Dry Dock Company in Oakland orders 25 guns. And then, in what feels like vindication, Mare Island Naval Shipyard places an order for 60 guns and 20,000 studs. Ted asks who is handling the purchase order for Mare Island. The purchasing agent tells him it is being processed through Lieutenant Morrison's department. Ted allows himself a bitter smile. Morrison, who had dismissed his idea as impractical just 6 months earlier, is now buying the product Ted built after quitting. There is no apology from Morrison. No acknowledgement that Ted was right. Just a cold, official purchase order with a request for delivery as soon as possible. By the end of December 1941, Ted has more orders than he can possibly fulfill working alone in his small shop. He is completely overwhelmed. Orders are coming in faster than he can build products. He needs help. He needs a real factory. He needs employees. In January 1942, Ted makes a bold move. He leases a much larger industrial building in San Leandro, about 10 miles south of his current location. The building is huge compared to his workshop, maybe 10,000 square feet. It is an old warehouse that previously stored agricultural equipment. It sits in the middle of cornfields, isolated and plain. But it has everything he needs. High ceilings, heavy-duty electrical service, loading docks, office space, room to grow. Moving into this space is terrifying. The rent is 10 times what he was paying before. If business slows down, he will not be able to afford it. But business is not slowing down. It is accelerating. He hires his first employees in February 1942. 5 men to start. He teaches them how to assemble the welding guns, how to manufacture the flux caps, how to test each unit. Production increases immediately. By March, he has 20 workers. By June, 50. By September, 150. The San Leandro factory operates around the clock now, just like the shipyards. 3 shifts, 7 days a week. There are no holidays. No days off. Everyone understands what is at stake. The factory produces welding guns at a rate of about 30 per day. Stud production reaches thousands per day. Every major shipyard on the West Coast is now using Nelson stud welding equipment. And the feedback from the shipyards is extraordinary. The results are better than Ted even hoped. A submarine deck installation that previously required 12 workers and 6 days can now be completed by 3 workers in 1 day. 1 day versus 6 days. That is an 80% reduction in time. And those 3 workers do not need to build scaffolding, so you save another 2 days there. The elimination of scaffolding has other benefits too. Those 12 workers who were previously spending a week on deck installation can now be assigned to other tasks. Welding hull plates, installing equipment, running electrical cables. The labor savings ripple through the entire construction process. The welds themselves turn out to be superior to the old bolted connections in several ways. The studs cannot work loose like bolts can. There are no threads to strip or corrode. The welds are actually stronger than bolted connections in tensile strength tests. And if a wooden deck plank ever needs to be removed for maintenance or repair, you can simply unscrew it from the studs and then screw it back down when you are done. No need to drill new holes or install new bolts. At Mare Island Naval Shipyard, submarine construction times start dropping significantly. The yard completes 17 submarines between 1941 and 1945, and the construction time for each boat gets progressively shorter as they implement new efficiency methods. Stud welding is not the only innovation, but it is a major contributor to the time savings. By mid-1942, the application of stud welding has expanded far beyond just deck planking. Engineers at various shipyards start finding new uses for the technology. Pipe hangers can be stud welded to bulkheads instead of bolted, saving time and providing stronger attachment. Cable support brackets can be stud welded in place. Equipment mounting brackets can be stud welded. Anywhere you need to attach something to a steel structure, stud welding offers a faster and often stronger solution. The Navy Bureau of Ships, the same organization that had shelved Ted's proposal for 18 to 24 months of review, is now intensely interested in his process. They send engineering teams to observe the stud welding operations at various shipyards. They conduct tests on weld strength, fatigue resistance, corrosion resistance, and behavior under extreme stress. They test how the welds hold up after exposure to salt water, to temperature cycling, to vibration. The results of all this testing confirm what Ted knew from the beginning. His welds are not just faster than traditional bolted connections. They are actually superior in almost every measurable way. The only real disadvantage is that you cannot easily remove a welded stud if you make a mistake. With a bolt, you can just unbolt it and start over. With a weld, you have to grind it off and weld a new stud. But this turns out to be a minor issue compared to the enormous advantages. On November 19, 1942, Just 11 months after Ted quit his $11 a day job at Mare Island, he receives a visit that feels surreal. 5 Navy officers in full dress uniforms arrive at his San Leandro factory unannounced. Ted is wearing his usual work clothes, tan pants and a button-up shirt with grease stains on it, when his secretary tells him there are Navy officers here to see him. He walks to the front office, wondering if maybe there is a problem with one of the orders. But the officers are smiling. The senior officer, a captain named Harrison, introduces himself as representing the Bureau of Ships. Mr. Nelson, Captain Harrison says formally, I am here to inform you that the Navy has completed a comprehensive evaluation of your stud welding process. We have analyzed its use across multiple shipyards and vessel types over the past 10 months. Our engineers have concluded that your invention has saved the United States Navy an estimated 5 million man-hours in submarine and surface ship construction during this period. Ted is stunned. 5 million man-hours. He had known his system was saving time, but he had never tried to calculate the total across all the shipyards using it. Captain Harrison continues. That number is expected to increase substantially as more shipyards adopt your technology and as we expand its use to additional applications. Your invention is making a significant contribution to America's ability to build naval vessels quickly in this time of war. He pauses, then says, on behalf of the Secretary of the Navy and the United States government, I am authorized to present you with this citation for exceptional contribution to the war effort. One of the other officers steps forward with a framed certificate. Ted takes it, not quite sure what to say. He is proud, certainly. Vindicated, absolutely. But he is also thinking about Morrison and Hartwell and all the people at Mare Island who dismissed his idea without serious consideration. Captain Harrison seems to read his expression. I understand you submitted a proposal to Mare Island in early 1941, Mr. Nelson. I have personally reviewed that file. Your proposal was not properly evaluated at the time. That was a mistake, and I apologize on behalf of the Navy. It is the first time anyone from the Navy has acknowledged that they were wrong. Ted feels some of his anger melting away. However, Captain Harrison continues, your decision to develop the technology independently has actually resulted in faster deployment than would have been possible through our normal procurement process. Our acquisition procedures are necessarily thorough, but they are also slow. Sometimes, the best way to serve your country is to ignore official channels and just solve the problem. You have certainly done that, Mr. Nelson. Ted finally finds his voice. Thank you, sir. I just wanted to help. I could see we were wasting time, and I knew there was a better way. After the officers leave, Ted hangs the citation on the wall of his office. His employees gather around to look at it and congratulate him. But there is no time for extended celebration. There are orders to fill. Welding guns to build. A war to win. The months roll on. The war intensifies. American forces are fighting in North Africa, preparing for invasions of Europe and island-hopping campaigns across the Pacific. The demand for ships continues to climb. Ted's company keeps growing. In March 1943, Ted opens a second manufacturing facility, this time on the East Coast in Camden, New Jersey. This plant is specifically designed to supply shipyards in the northeastern United States. The Navy has shipyards in Portsmouth, New Hampshire, Philadelphia, Norfolk, Virginia, Charleston, South Carolina. All of these yards are now building submarines, destroyers, and other vessels at an accelerated pace. Having a manufacturing plant nearby reduces shipping costs and delivery times. The Camden plant is larger than the San Leandro facility, about 20,000 square feet. Ted hires a plant manager to run it since he cannot be in two places at once. By mid-1943, the two plants together employ over 400 workers and generate approximately $4 million in annual revenue. Despite the success, Ted remains remarkably modest. He still spends most of his time in the factories, usually in work clothes, often operating equipment alongside his employees. He pays himself a salary of $1,000 per month, which is comfortable but not extravagant. All profits get reinvested into the business, buying better equipment, expanding production capacity, and paying down the loan from the Reconstruction Finance Corporation. The impact of stud welding on the war effort continues to grow exponentially as more applications are found and more shipyards adopt the technology. By 1943, stud welding is standard practice not just at submarine yards but at every type of naval construction facility in the country. The Essex-class aircraft carriers, which form the backbone of America's fast carrier task forces in the Pacific, use Nelson stud welding extensively. These massive ships have flight decks covering tens of thousands of square feet. The flight deck consists of wooden planks installed over steel framework, exactly the kind of application where stud welding excels. Each Essex-class carrier requires approximately 20,000 studs for flight deck attachment alone, plus thousands more for interior fittings, equipment mounts, and other applications. The Navy builds 24 Essex-class carriers during the war. That is close to 500,000 studs just for this one class of ships. The Iowa-class battleships, the most powerful battleships ever built by the United States, use stud welding for deck planking, equipment mounts, and various armor attachment points. These ships are enormous, over 800 feet long, with complex internal structures and countless attachment points. The Baltimore-class heavy cruisers incorporate stud welding throughout their construction. So do destroyer escorts, patrol boats, landing ships, and every other type of vessel the Navy builds. But the most remarkable impact remains in submarine construction. This is where Ted's innovation started, and it is where the time savings are most dramatic. Portsmouth Naval Shipyard in New Hampshire becomes the most prolific submarine builder in American history during World War II. The yard completes 79 submarines between July 1940 and July 1945. 79 submarines in 5 years. That averages out to more than one submarine per month, although production was actually heavily concentrated in the later war years as methods improved. Portsmouth's success is built on many innovations. Modular construction techniques, prefabricated sections, specialized work teams. But stud welding is a critical enabling technology that makes many other efficiencies possible. The yard adopts Ted's system early and uses it aggressively, not just for decking but for hundreds of other attachment points throughout each submarine. The result is visible in stunning production statistics. On January 27, 1944, Portsmouth launches 4 submarines in a single day. The Redfish, Ronquil, Razorback, and Scabbardfish all hit the water on the same day. 4 submarines in one day. To put that in perspective, Germany's entire submarine production for the month of January 1944 was about 16 boats. Portsmouth produced 1/4 of Germany's monthly submarine output in a single day. At peak production in 1944, Portsmouth completes 32 submarines. That is one submarine approximately every 11 days. The construction time from laying the keel to commissioning the boat averages about 12 months at Portsmouth for the standard Balao-class submarines. Other yards building the same class of submarine typically need 14 to 16 months. Electric Boat Company in Groton, Connecticut builds 74 submarines during the war. They also adopt stud welding extensively. Manitowoc Shipbuilding in Wisconsin, incredibly, builds 28 submarines despite being located on the Great Lakes hundreds of miles from the ocean. These submarines are built in sections, floated down the Mississippi River on barges, and assembled near the Gulf of Mexico. Even these unusual logistical circumstances benefit from stud welding because the modular sections can be fitted out more quickly. Across all shipyards, the United States constructs 203 submarines during World War II. Each submarine requires thousands of individual stud-welded attachment points. Calculating conservatively, if each submarine uses 5,000 studs, which is probably low, that is over 1 million studs for the submarine fleet alone. If each stud saves just 10 minutes compared to the old bolted method, that is 10 million minutes, or about 167,000 hours, or about 19 years of continuous work. And that is just for submarines. The actual time savings across all ship types is much, much larger. But submarines represent only a fraction of overall ship production. The real volume is in merchant vessels and amphibious craft. The Liberty Ship Program, managed by the Maritime Commission and built primarily at the Kaiser shipyards, produces 2,710 cargo ships during the war. This is one of the most remarkable industrial achievements in human history. Each Liberty ship is a standardized cargo vessel, about 440 feet long, designed to be built quickly using mass production techniques. The ships are welded rather than riveted, which is itself a major innovation. They are built in modular sections that are pre-fabricated and then assembled. And they use stud welding extensively. A typical Liberty ship requires approximately 5,000 to 8,000 stud welded attachments. Wooden deck planking accounts for some of these. Cargo handling equipment requires hundreds of studs for mounting winches, davits, and other gear. Defensive gun mounts, installed on every Liberty ship to fight off aircraft and submarines, are stud welded in place. Ship fittings of all kinds use stud welded attachments. The pace of Liberty ship production reaches absolutely insane levels by 1943. At the peak of production, American shipyards are launching 3 new Liberty ships every single day. 3 complete ocean-going cargo ships per day. That is 90 ships per month. Over 1,000 ships per year. This scale of production is unprecedented in all of human history up to that point. This is only possible because of radical innovations in every aspect of ship construction. Prefabrication allows ship sections to be built in different locations and then quickly assembled. Modular design means workers can specialize in particular tasks rather than needing to know every aspect of shipbuilding. Welding instead of riveting speeds construction dramatically. And stud welding allows attachments to be installed in a fraction of the time previously required. The strategic importance of this production cannot be overstated. Germany's submarine campaign in the Atlantic is trying to sink Allied merchant ships faster than they can be replaced. For the first 2 years of the war, the Germans are succeeding. U-boats are sinking ships faster than British and American shipyards can build them. But by 1943, American production has reached such a scale that the equation flips. Now the Allies are building ships faster than Germany can sink them. This turns the Battle of the Atlantic decisively in favor of the Allies. Every ship built faster because of stud welding contributes to this strategic shift. Every day a ship reaches service sooner is another day it can carry troops, tanks, ammunition, food, fuel, and all the other supplies needed to fight a global war. The time savings from Ted Nelson's invention translates directly into strategic advantage. The Victory ships, a more advanced version of the Liberty ship design, also use stud welding extensively. These ships are faster and more capable than Liberty ships but still built using mass production methods. Several hundred Victory ships are completed during and immediately after the war. Landing craft represent another enormous category of vessels where stud welding proves invaluable. The amphibious invasions that characterize much of World War II strategy, from North Africa to Sicily to Normandy to countless Pacific islands, all require specialized landing craft. These are flat-bottomed boats designed to run up onto beaches and discharge cargo directly onto shore. The most common types are LSTs, landing ship tanks, which can carry tanks and heavy vehicles. LCIs, landing craft infantry, designed to carry troops. LCMs, landing craft mechanized, for medium vehicles. And LCVPs, landing craft vehicle personnel, the famous Higgins boats that you see in every D-Day movie. Thousands of these craft are built during the war. They are crude vessels compared to ocean-going ships. Speed and elegance are not priorities. But they need to be built quickly and reliably. Cargo ramps have to be strong enough to support tanks. Davit mounts have to handle repeated loading and unloading cycles. Deck fittings have to withstand the pounding of waves and the grinding of beaching operations. Stud welding proves ideal for landing craft construction. Ramps can be hinged on stud-welded mounting points. Davits for cargo handling are stud-welded to deck structures. Interior fittings throughout the craft use stud-welded attachments. The speed of installation allows landing craft to be built at a pace that would have been impossible with traditional bolted construction methods. The D-Day invasion of Normandy on June 6, 1944 provides a dramatic illustration of the scale of landing craft production. The invasion fleet includes approximately 7,000 vessels. Not all of these are landing craft, many are warships providing fire support and protection. but several thousand are landing craft of various types. This armada, the largest amphibious assault in history, is only possible because American and British shipyards have produced landing craft in vast numbers. After victory in Europe in May 1945, all attention shifts to the Pacific and the planned invasion of Japan. Operation Downfall, as the invasion plan is called, envisions two massive amphibious assaults. The first, Operation Olympic, is scheduled for November 1945 and would land on the southern Japanese island of Kyushu. The second, Operation Coronet, is planned for March 1946 and would target the Tokyo area on the main island of Honshu. The scale of these planned operations is staggering. The Navy estimates it would need even more landing craft than were used at Normandy. Shipyards begin preparing for another surge of production in summer 1945. Ted's factories receive preliminary orders for additional welding guns and millions of studs. Then atomic bombs destroy Hiroshima on August 6 and Nagasaki on August 9. Japan surrenders on August 15, 1945. World War II ends. The invasion of Japan never happens. Almost overnight, the massive military production machine begins shutting down. Contracts are cancelled. Workers are laid off by the hundreds of thousands. Shipyards that employed tens of thousands of workers scale down to peacetime operations or close entirely. The Nelson Specialty Welding Equipment Corporation suddenly faces an existential crisis. Military orders, which have been the entire basis of the business for almost 4 years, dry up almost instantly. The two factories, San Leandro and Camden, employed over 400 people at peak production. Now there is barely enough work to keep 50 people busy. Ted has to make painful decisions about layoffs. These are people who have worked incredibly hard for the war effort. Many have become friends. But there simply is not enough business to keep everyone employed. In late 1945 and early 1946, Ted spends sleepless nights worrying about whether the company will survive. The loan from the Reconstruction Finance Corporation has been mostly paid off, but there are still obligations. The factory leases still have to be paid. Equipment purchased during the war years represents a significant investment that is now sitting mostly idle. But Ted has been preparing for this moment, at least mentally. During the war years, even as he worked 16-hour days filling military orders, he has been thinking about peacetime applications for stud welding. The technology is not limited to shipbuilding. Any industry that fabricates steel structures could potentially benefit. Construction is an obvious market. Buildings, bridges, industrial facilities, all use steel frameworks that require countless attachment points. Stud welding could speed construction and potentially provide stronger connections than traditional methods. The automotive industry might be interested for attaching components to vehicle chassis. Manufacturing plants use steel structures throughout, offering opportunities for stud welding. Storage tanks and pressure vessels require numerous attachments. Oil refineries and chemical plants have extensive piping systems that need hangers and supports. Ted begins a second transformation of his company, this time from wartime military supplier to peacetime industrial equipment manufacturer. It is a difficult transition. The construction and manufacturing industries are not in crisis mode the way the military was during the war. They are not desperate for faster methods. They have established suppliers and established procedures. Convincing them to try something new requires patience and persistence. Ted travels extensively in 1946 and 1947, visiting construction companies, steel fabricators, and industrial plants. He demonstrates his equipment. He explains the cost savings. Slowly, gradually, orders begin to come in from civilian customers. A bridge builder in Pennsylvania orders welding guns for a project. A tank manufacturer in Ohio starts using stud welding for pipe hanger installation. A construction company in Texas adopts the technology for a large building project. The civilian market grows slowly but steadily. By 1948, Ted's company has successfully transitioned to peacetime production. The business is much smaller than during the war. The San Leandro plant operates with about 80 employees. The Camden plant has 50. Revenue is perhaps 1/5 of what it was at the wartime peak. But the company is stable, profitable, and growing gradually. The post-war construction boom helps significantly. America is building suburbs, highways, schools, shopping centers, office buildings. All of this construction requires steel work. All of it creates opportunities for stud welding applications. As more contractors try the technology and see the benefits, word spreads. By 1950, Nelson stud welding equipment has a solid reputation in the construction and industrial fabrication industries. In 1950, Ted receives an offer to sell his company to TRW, a large industrial conglomerate with diverse holdings in automotive, aerospace, and industrial equipment. The offer is generous. TRW wants to add stud welding technology to its product portfolio and expand sales globally. Ted is now 55 years old. He has been working intensely for 9 years building this company. The offer would make him financially secure for the rest of his life and allow him to retire from the day-to-day grind of running a business. After discussing it with Emma, Ted accepts the offer. The sale closes in late 1950. Ted remains as a consultant for a few years to help with the transition, but he steps back from active management. The Nelson name stays on the product line. TRW markets the equipment as Nelson Stud Welding Systems, maintaining the brand recognition that Ted built. Ted and Emma buy a comfortable house in a quiet neighborhood in Oakland. For the first time in his adult life, Ted does not have to work unless he wants to. He spends time on hobbies. He and Emma travel, visiting places they had only read about in books. He stays in touch with some of his former employees and occasionally visits the factories to see how things are going. Over the following decades, the stud welding technology Ted pioneered continues to evolve and expand. The company changes hands several more times as it gets bought and sold by various corporations. TRW sells the division to Facentech in 2000. Doncaster's Group acquires Facentech in 2007. Stanley Black & Decker purchases the Industrial Fastening Division in 2018. Through all these corporate transformations, the Nelson brand persists. Even today, the product line is marketed as Nelson Stud Welding. Modern stud welding is considerably more sophisticated than Ted's original garage prototype. Inverter-based power supplies provide extremely precise control over welding current and arc timing, allowing for consistently perfect welds. Automated and robotic welding systems apply studs at high speed in manufacturing environments. Automotive assembly plants use robotic stud welding extensively, with machines capable of welding dozens of studs per minute. Portable battery-powered stud welding guns allow construction workers to operate in remote locations without needing access to electrical outlets. The range of available stud sizes and types has expanded enormously. You can get studs from a few millimeters long to several inches long. Different thread patterns. Different materials including stainless steel, aluminum, and exotic alloys for specialized applications. Flux cap chemistry has been refined to work with different base metals and different welding conditions. But despite all these refinements, the fundamental principle remains exactly the same as what Ted Nelson invented in his garage in 1941. A metal stud with a ceramic flux cap. A spring-loaded gun that presses the stud against the base metal. An electrical arc that melts both surfaces and fuses them together. 1 second per stud. No access needed from the backside. Simple, fast, and strong. The applications have expanded into virtually every industry that works with metal. Construction workers use stud welding to attach metal floor decking to steel beams in skyscrapers. Instead of drilling holes and bolting the decking down, which would take hours, they simply stud weld the decking in place in minutes. Bridge construction uses stud welding for guardrail posts, lighting mounts, and sign supports. Nuclear power plants use it extensively for cable tray supports and equipment mounting throughout the facility. The demanding safety requirements of nuclear plants mean that every welding procedure is rigorously tested and documented. Stud welding has passed all these tests and is approved for use in nuclear facilities worldwide. Oil refineries and chemical plants use stud welding for pipe hanger supports throughout their extensive piping systems. A single large refinery might have hundreds of miles of pipe that need to be supported and secured. Stud welding allows these supports to be installed quickly and reliably. Automotive manufacturers use stud welding throughout vehicle assembly for electrical grounding points, trim attachment studs, and various mounting points. Modern cars have dozens of stud-welded attachment points installed by robots during assembly. The shipbuilding industry, where Ted's invention started, continues to use stud welding extensively. Modern naval vessels and commercial ships still use the technology for deck attachment, equipment mounting, and countless other applications. The basic problems Ted identified in 1941, the need to attach things to steel structures quickly and reliably, still exist. His solution still works. Perhaps the most touching testament to Ted's legacy comes from historic ship restoration projects. The battleship Texas, commissioned in 1914 and one of only 7 ships to serve in both World Wars, is currently undergoing extensive restoration. The ship is over a century old and requires massive amounts of repair work to preserve it for future generations. The restoration team uses modern Nelson stud welding equipment to install new steel plates and repair corroded sections. They are using the same technology Ted invented 80 years ago to repair a ship that was already 30 years old when Ted was born. The submarine USS Pampanito, a World War II Balao-class boat that Ted's invention helped build faster, is now a museum ship in San Francisco. The boat is moored at Pier 45 near Fisherman's Wharf and welcomes over 100,000 visitors every year. Maintaining a 75-year-old submarine requires constant work. The volunteer restoration crew uses Nelson stud welding equipment for ongoing maintenance and repairs. There is something beautifully circular about this. A technology invented to build submarines faster during the war is now being used to preserve one of those submarines for future generations to see and learn from. Ted Nelson lived to see his invention's impact extend far beyond anything he imagined that day in 1941 when he first sketched his idea in a notebook. He saw stud welding become standard practice in shipbuilding. He saw it adopted by industries worldwide. He saw his name become synonymous with an entire category of welding technology. He lived long enough to know that his simple idea, rejected by Navy bureaucrats as impractical, had fundamentally changed multiple industries and helped America win the most important war in history. Ted died in 1994 at the age of 89. Emma had passed away a few years earlier. They had been married for over 60 years. Ted's obituary in the local newspaper was brief, mentioning his service as a welder during World War II and his later success as a business owner. It did not mention the 50 million man-hours saved. It did not describe how his invention helped win the war. Most people who read the obituary had no idea of the impact this quiet, modest man had made on history. The statistics of his achievement tell an important part of the story, but not the complete story. 50 million man-hours saved in naval construction. 2 Army-Navy awards for production excellence. Thousands of ships built faster because of his technology. Billions of studs manufactured over the decades. These are impressive numbers. But numbers alone cannot capture the full human impact. Behind those statistics were individual human beings whose lives were affected. Sailors who came home from the war because their submarine was completed in time to join the fleet and complete successful patrols. Marines who survived amphibious assaults because enough landing craft were available to get them ashore quickly. Families who were not shattered by loss because the war ended sooner due to overwhelming American industrial production. Workers who avoided injury because they did not have to spend hours balanced on scaffolding in cramped spaces below decks. The true measure of innovation is not just efficiency gained or money saved. It is the positive impact on human lives. Ted Nelson, the $11-a-day welder who was told his idea was impractical, saved more lives than most combat heroes. He did it not with weapons but with welding. Not through destruction but through construction. Not by taking life but by enabling others to preserve it. The rejection Ted faced was not unique in the history of innovation. Countless inventors and innovators have been dismissed by established authorities who are invested in maintaining the status quo. The Wright brothers were told by respected scientists that powered heavier than air flight was impossible. Henry Ford was laughed at when he suggested that cars could be mass-produced affordably enough for average families to own them. Chester Carlson, who invented photocopying, spent years trying to sell his idea to companies that all told him nobody would want to make copies of documents. Robert Goddard, pioneer of liquid-fueled rockets, was mocked by the New York Times for suggesting rockets could work in the vacuum of space. What made Ted Nelson different was not the quality of his idea, although it was a very good idea. What made him different was his refusal to accept rejection as final. He did not spend years arguing with bureaucrats. He did not write endless letters trying to convince skeptics. He simply quit his job, risked everything he had, built his invention, proved that it worked, and let the results speak for themselves. This is a pattern we see repeatedly in the history of innovation. The most important breakthroughs often come from people working outside the established system because the system has rejected them. They innovate not through official channels but in spite of official channels. And once they prove their concept works, the system that rejected them suddenly wants to adopt it and pretend they were supportive all along. Mare Island Naval Shipyard, where Ted worked as an $11 a day welder and where his idea was dismissed as impractical, closed permanently in 1996 after 142 years of operation. Over its long history, the yard built 512 ships including 44 submarines. The base was an important part of American naval history, serving through the Civil War, Spanish-American War, both World Wars, and the Cold War. At its peak during World War II, Mare Island employed nearly 50,000 workers and operated as a complete industrial city with its own power plant, hospital, fire department, and housing. The closure of Mare Island was part of a larger wave of base closures following the end of the Cold War. The Navy no longer needed as many shipyards as it did during the years of competition with the Soviet Union. The decision to close Mare Island was controversial and painful for the community of Vallejo, which had grown up around the base and depended on it economically. Today, the former Mare Island Naval Shipyard is being slowly redeveloped as a mixed-use area with commercial businesses, residential housing, and preserved historic buildings. Some of the historic structures have been designated as California State Historical Landmarks and National Historic Landmark sites. Walking through the old base, you can still see the massive dry docks where submarines and ships were built and repaired. The old machine shops and fabrication buildings, some dating back over a century. The chapel where workers worshipped. The commanding officer's residence with its view over the bay. In one of the preserved buildings, there is a small museum dedicated to Mare Island's history. The museum has exhibits about the various ships built there, the different eras of the base's operation, and the workers who made it all possible. There are tools, photographs, uniforms, and artifacts from over a century of naval shipbuilding. But there is no exhibit about Ted Nelson. No monument to the welder who saved 50 million man-hours. No recognition of the man whose simple invention changed naval construction forever. His story has been largely forgotten, except among welding professionals who study the history of their craft and maritime historians who dig deep into the technical details of World War II shipbuilding. This anonymity would probably not have bothered Ted. By all accounts, he was not seeking fame or glory. He was not trying to become a celebrated inventor or rich industrialist. He was simply solving a problem that frustrated him. He was trying to make things work better. He was doing his part to help his country prepare for and ultimately win a war. The fact that his solution worked brilliantly, that it saved enormous amounts of time and labor, that it changed an entire industry, those outcomes were satisfying. But they were not the goal. The goal was just to fix something that was broken. This kind of humble, problem-focused innovation is actually more common than we might think. Throughout history, many of the most important innovations have come from working people who saw inefficiencies in their daily work and figured out better ways to do things. Not because they were geniuses. Not because they had advanced degrees or special training, but because they understood the practical realities of the work, they could see what was wasted effort, and they had the technical knowledge to devise solutions. The lesson here is important for every generation. Innovation often comes from unexpected places and unexpected people. Not necessarily from credentialed experts at the top of their fields, but from working people who deal with problems every single day and understand them intimately. Not from corporate research laboratories with big budgets, although those certainly produce innovations too, but from garage workshops where individuals tinker and experiment with their own time and money. Not through official channels and bureaucratic processes, but from people who are willing to work outside the system when the system refuses to listen. The next great innovation that changes an industry or saves countless hours of labor might come from anywhere. It might come from a welder in a shipyard who sees a better way to attach things. A mechanic in an auto repair shop who invents a better tool. A nurse in a hospital who figures out a more efficient patient care procedure. A teacher in a classroom who develops a better way to help students learn. A construction worker who devises a safer scaffolding system. A warehouse worker who streamlines inventory management. These are not people with PhDs or fancy titles. They are people who do the work, who see the problems firsthand, and who have the practical knowledge to develop solutions. History suggests very strongly that we should pay attention when these people propose innovations. We should listen with open minds. We should be willing to test their ideas rather than dismissing them because they come from unexpected sources. Not every idea from a frontline worker will be revolutionary. Most will be modest improvements. Some will not work at all. But the occasional idea that does work, the idea that genuinely solves a real problem in a dramatically better way, that idea can change everything. And we will never know which ideas are the transformative ones unless we are willing to seriously consider them. Ted Nelson's ceramic flux cap was just a small piece of ceramic, barely an inch across, filled with chemical powder. His welding gun was just a simple mechanical device, not much more complex than a heavy-duty stapler. But combined, they eliminated the need for scaffolding, reduced installation time by 80% or more, increased worker safety, improved weld quality, and accelerated ship production at the most critical moment in the 20th century. 50 million man-hours. Think about that number again. 50 million hours is approximately 5,700 years. If you started working 8 hours a day, every single day including weekends and holidays, starting at the beginning of recorded human history, you still would not have worked 50 million hours by now. That is how much cumulative time Ted Nelson's invention saved. And this number only represents the direct construction time savings during World War II. It does not account for the strategic impact of getting ships into service faster. It does not measure the lives saved because submarines reached combat zones sooner and could interdict enemy shipping earlier. It does not calculate the morale effect of American industrial production exceeding all expectations and demoralizing the enemy. It does not quantify how the mere existence of rapidly growing American naval power deterred some enemy actions and forced strategic decisions. The full impact of Ted Nelson's invention cannot be calculated with precision. But we can say with absolute certainty that America's victory in World War II depended critically on industrial capacity and production efficiency. The battles at sea and on land were won by the courage and skill of soldiers, sailors, airmen, and Marines. But the war as a whole was won by the industrial base that supplied those fighting forces with ships, planes, tanks, ammunition, food, fuel, and every other necessity of modern warfare. People like Ted Nelson, who found ways to make that industrial base more efficient, more productive, faster, were essential to victory. They were not on the front lines. They were not in combat. Most received no medals or public recognition. But their contributions were absolutely vital. They understood that in a total war involving the entire industrial capacity of nations, every minute saved in production translated directly or indirectly into combat advantage. Ted Nelson asked a simple question in 1941. There has to be a better way. Why are we wasting so much time and labor on this inefficient process? His answer to that question helped win the most important war in human history. What questions are you asking today as you go about your work, whatever that work might be? What processes seem inefficient or wasteful? What problems keep recurring that nobody seems to address? What solutions can you imagine that might work better than current methods? And perhaps most importantly, when you propose those solutions and people in authority tell you it cannot be done, when bureaucrats tell you to follow established procedures, when experts dismiss your idea as impractical or impossible, will you have the courage that Ted Nelson had? Will you be willing to risk something to prove your idea works? The history of innovation teaches us that sometimes the most important thing you can do is ignore the experts who tell you something is impossible. Trust your own observations of the real world. Trust your own technical knowledge of how things actually work. Trust your own judgment about whether a solution is viable. Then build it. Prove it. Let the results speak for themselves. Ted Nelson did exactly that. He went from being an $11-a-day welder, dismissed and ignored by Navy officials, to becoming an industrialist whose technology changed multiple industries and saved his country. But more importantly than the financial success or the recognition, he had the satisfaction of knowing he was right. He saw a problem. He knew the solution. And despite everyone telling him he was wrong, he proved that his idea worked. That satisfaction, that validation, that sense of having contributed something genuinely valuable to the world, those are rewards that cannot be measured in money or awards. 80 years after Ted Nelson first sketched his idea in a notebook, welders around the world use his invention thousands of times every day. Construction workers building skyscrapers. Shipyard workers building vessels. Automotive assembly line robots building cars. Bridge builders, industrial fabricators, maintenance workers in every kind of facility. They pull the trigger on stud welding guns, descendants of Ted's original design, and they probably never think about the man who invented the technology or the story of how it came to exist. And somewhere today, perhaps in a garage or workshop, perhaps in a factory or construction site, the next Ted Nelson is looking at an inefficient process and thinking, there has to be a better way. That person is sketching ideas, experimenting with solutions, getting ready to approach people in authority with a proposal. And there is a very good chance those people in authority will dismiss the idea. They will say it is impractical. They will say if it could be done, someone would have done it already. They will say, follow established procedures. But if that person has Ted Nelson's determination, if they refuse to accept rejection, if they are willing to risk something to prove their idea works, then maybe, just maybe, they will create the next innovation that changes an industry and makes the world work a bit better. The best innovations do not come from people who wait for permission. They come from people who see problems, know how to fix them, and refuse to take no for an answer. Ted Nelson proved that. His story is proof that one person with a simple idea and the courage to pursue it can genuinely change the world. If you found this story inspiring, make sure to subscribe to the channel for more incredible tales of innovation, persistence, and people who changed history against all odds. Hit the like button to help others discover this story. And leave a comment sharing your thoughts. What inefficiency do you see in your work or life that you wish someone would fix? Maybe you will be the one to fix it. We will be back soon with another fascinating journey through history. Thanks for watching.